Hello, I'm going to try to teach you how to do cotangent x and then cosecant x and secant x. As you can see, we have a lot of things going on the board, but I wanted you to have a quick reference. So tan x, remember, is sine x divided by cosine x. Since you're dividing by cosine x, whenever cosine x is 0, we're going to have asymptotes. And if you use your unit circle over here, you can see that cosine will be 0 at pi over 2, 3 pi over 2, and then again and again. And that's the rhythm we got going there, and also going in the negative. When the numerator is 0, so when sine x is 0, then the whole fraction is 0. And so that happens at the x-intercepts, because what makes 0 in the numerator is always our x-intercepts. And if you come over here, sine, which is the y-coordinate, is 0 at 0 and pi. Sine x, as you know, and cosine x, I'm going to leave up here and talk about them when I go to those graphs. So let's do cotan. Cotan is the flip of tan. So now my numerator is cosine x. So what makes 0 in my numerator will be my x-intercepts. So let's see, cosine is 0 at pi over 2 and 3 pi over 2. So let's put a couple dots here. Pi over 2 and 3 pi over 2. Let me spread that out just a bit more. Get a little bit more there. I think I got it too crowded. Okay, and then now look to the denominator. The denominator, when it's 0, and as long as it doesn't cancel out, and of course these guys don't cancel out, cosine x and sine x only have the same values every once in a while, but never, they're never going to make a 1, so they're never going to cancel. So that means what makes 0 in the denominator? Domain errors, right? Those make vertical asymptotes, so we're not varying from things we've learned before. So let's put a couple vertical asymptotes in. Sine x is 0 at 0 and pi, and then at 2 pi. And so we're going to have an asymptote on the y-axis, or y0. We're going to have one at pi. We're going to have one at 2 pi, and we're going to have another one, etc., out here. So let's see, let's label those. We got one at 0, one at pi, and then we circle back, hit 2 pi again. Okay, and this is, of course, when x equals 2 pi, to be very clear. And then we got 3 pi. So you can see we're going to have x-intercepts right here in the middle. On the half pi's is one way to think about it. And on the integer pi's, we're going to have the asymptotes. Now, how does the graph look? Does it look like this tan graph, or does it look any different? Let's do a small investigation here. So when sine x is really, really small, when the denominator is really small, then the cosine is getting closer and closer to 1 or something, then this becomes a large number. So when sine x is really small, well, sine x is really small, like right here it's really small, and again right here, and then over here it's negative and small and negative and small. So just past 0, sine x is positive and small. That means this graph wants to go positive infinity. If the denominator's really, really small, and we divide into a number like 1 or something close to 1, and look what x is right there, then this guy's going to be a very big value. So it explodes up. And then as we get close to pi, okay, now all of a sudden the x is negative, so cosine is negative, and now we've got a very large negative number, and we're just going to connect the curves just like we would when we discovered the tan graph. So I'm going to assume in mathematics, it's true, that there's not too much variation here now that we got the rhythm of it. And this is our cotan graph. Sorry, it's not very pretty. Yours doesn't have to be either. Okay, same idea here. Where the x-intercepts are here, well, when you flip them over, you get 1 over. Those are going to be asymptotes. And so we're going to have asymptotes every time we have x-intercepts. So for cosecant, at negative pi, asymptote. At pi, asymptote. It's supposed to be an x-intercept there at 0 too. And at 0, asymptote. Over here, let's just go ahead and put some asymptotes in. Make sure we label them. And this is key for the homework. You're going to take pictures, so you're going to want to label things. Over here, we got negative pi over 2. Negative pi over 2, that's an x-intercept. So when we divide by 0, the output here at this intercept, that'll be 0. Okay, what makes 0 is the x-intercept, and that's going to make asymptotes. Okay, we got them at pi over 2, negative pi over 2. And another one over here at 3 pi over 2. Okay, now what does the graph do? What does the graph do? Well, let's label the most obvious point we have. Most obvious point we have right here, right there, and right here. Well, that's when the output's 1. And when you do 1 over 1, you get 1. So we know this graph hits 1 right here at pi over 2. And the x is pi over 2. So that's an x coordinate of pi over 2 and a y coordinate of 1. Again, these labels are going to be important. Let's see, this guy's negative 1 down here. So the flip of negative 1, going to be down here, is negative 1. And that one's at the 3 pi over 2. So we've got a x coordinate of 3 pi over 2. 3 pi over 2. It's not drawn very well. Sorry about that. Okay, 3 pi over 2. And we have negative 1 is the y. All right, now let's see. Let's get another one. There's a negative 1 right there. What is the graph going to do? Well, let's look at when sine of x is very small. This makes a giant number. So when is sine of x very small? Well, it's very small again, right here, when it's just past 0. So when I'm just past x equals 0, like, little notches past x equals 0, and I plug and chug these numbers, that makes the denominator very small. Because look, it's a tiny height, tiny height. There's a visual answer to all this stuff. That's why I always focus back on it. So that means I'm going to get a giant number here. Okay, so like 1 over, 1 over 100. Be a giant number, 100. So that graph is going to explode up. Okay, so let's just curve it down and hit this dot. What happens as we get close to pi again? Well, sine x is still positive and still tiny. So this thing is going to explode up again. And that's what these graphs do. They make these U's. This one is the same thing, but since sine x is negative, it's going to explode down. And that's what goes on with these graphs. Okay, to speed up this video, I'm just going to kind of jump to it. We get the same idea. We get these 1s. Okay, we get these dots where cosine x is the y-intercept is 1. So if you flip 1, it is also going to make a 1. So now we're going to also, if we plug and chug tiny numbers here, okay, we're going to end up, when we get tiny cosine x values, we're going to get those tiny cosine x values, and I'm going to use the unit circle again. When is the x coordinate tiny? Really close. That's an x coordinate, right? If I come off to the right, that's x up here on the unit circle. So right here, these are very tiny values on each side of pi over 2. So that's basically what happens here. So let's see. Got to get this graph. Sorry about that. Let's take a look. I just finished off the secant graph, the secant x graph. And I finished off a few more asymptotes. I want to remind you that if I do 1 and 2 loops, so if I do 1 u up and 1 u down, that's 1 full period. That's a 2 pi period. So right here on the secant graph, I've got basically 2 periods worth. I have a 1.5 periods over here on the cosecant graph. Both of these graphs have the same range, don't they? They both have a range where their y values are all the real numbers, but only, let's see, above 1 and equal to 1, comma, and all the y's less than or equal to -1. So that's the range of both of those. The domains have asymptotes every basically half, well, pi's apart, but on this one, every half pi's, there's asymptotes. So the domain has theirs here, and the domain's all reals over here, except for at the pi numbers. I know these are very sloppy, but when you look in your textbooks, you're going to see very nice versions of this. I just want to make sure you understand how they're built so that you're just not mimicking graphs, and understand the whole idea of when we divide by small numbers, that this graph explodes up to big numbers, because that's huge in calculus. That's limit questions when we get to calculus. Let me set up the next screen. Okay, I'm back. Let's try a couple graphs. These are ones similar to your homework, or actually ones off your homework. Just follow what I do and see if you can do the ones on the homework. I think at this one, on this task, you're going to take pictures and you want to show the small calculations that I show to make sure that we're not just taking them off Desmos. We're going to check them with Desmos, but I want to make sure you get a good understanding, and then we'll just use Desmos to double check it. Okay, cotan. If you notice, I copied and pasted our new Mama graphs right next to these guys so I can use them as reference because it makes it go a lot faster. First thing I'm going to do is get the period. Looks like the only thing going on in this problem is getting the period. If you look, the only thing I got is a 1/4 there. So normal period is pi. We're going to flip and multiply. That's 4 pi. Flip 1/4, multiply 4 pi. So normally the asymptotes are 0 and pi and 2 pi. And this is 2 periods up here in this parent graph. So one asymptote will still be at 0. Let me use a different color here. Okay, so we got an asymptote at 0. We're going to have an asymptote at then 1 period over. And that's 4 pi. Let's go ahead and do another period. Make another one over here. Negative 4 pi. Okay, there's no shifts or anything, so we're just going to sketch in the parent graph. It's key to make your churned, just for the artistic and for the calculus reasons. Yeah, there's a connection there. I'm going to draw this and curve it up until this dot, and then I'm going to curve it down. Concave up, inflection point, concave down. You don't need to know that word. It's a cool calculus word. Where are those x-intercepts? See if you can answer that question before I find them. 0, 4 pi, halfway, 2 pi, negative 2 pi. All right, let's do cosecant. Let's do cosecant. Okay, I got the parent graph right here. Let's get the asymptotes in the right place, and then I'm going to use these key dots and get the shifts right from there. The period's normally 2 pi. We're going to flip and multiply, so that's going to give us a new period of 6 pi. New period of 6 pi. Please forgive my fraction work. I'm doing it fast, but I want to get to the graphs. So if I put this calculation in, it is 2 pi divided by 1/3, and then I'm going to flip and multiply and get 6 pi. Okay, so I need to get an asymptote. That's 6 pi for 1 period. This period goes, let's look at this period right here. We're going to go from negative pi to pi. That's a 2 pi period. So let's do the same thing. Split 6 pi up. Let's split 6 pi up. We're going to make that 3 pi, negative 3 pi. Okay, let's use this dot, this one dot that's normally halfway between the asymptotes. Okay, halfway between the asymptotes. Oh, I forgot to put the 0 one. There's a 0 asymptote, excuse me. Okay, so halfway between the asymptotes, there's normally a dot that starts at 1. But we're not going to have that dot at 1. What are we going to do with that dot? That dot is going to get multiplied by 2, which is our amplitude still. So this dot is going to get, wherever it was 1, it's now going to get multiplied to 2. And then the graph wants to go up from there. But then it gets shifted down 1, down 1. That's a down 1. And this is our amplitude of 2. So if I take that dot that's normally at 1 and I expand it, I stretch it so it starts at 2, and then I bring it down 1, lo and behold, I'm right back where I started. So this is a dot that's on this graph. This dot is at, let's do the math again, halfway between 0 and 3 pi. So this dot is at 3 pi over 2, comma 1. Always label these key dots. And the graph should just explode up from there. Where is the graph on this side? So it's normally at negative 1, halfway between again. But it got stretched by 2, so it went over here to 2, and then it got dropped down by 1, and so it's way down there. There's the actual dot. I'm going to erase the other ones. All right, now this graph